thank you everyone for coming. My name is Elazar Leibovich. I worked in C++ for too many years, and I wanted to talk about debugging code you don't own, you don't build, you don't always have the source or the debug symbols. This is text from over 200 years ago, and the author of a book states before he, in the introduction, that everything in the book is well known and well established, but he still sees values with repeating known and useful things, and the same is still irrelevant to my talk. Everything is very well known, nothing is innovative, but it still makes sense to repeat useful things and known things. So before talking about how, we need to figure out why. Why that's interesting to debug a code you didn't write and you don't have all the resources to debug it. The best way to avoid a problem is to solve a problem is not to have to solve it in the first place. ICE, internal compiler error. Can anyone who experienced that in the recent year raise his hand or her? Okay, I see a couple of hands. My personal experience is that in C++ 98, where the language was simpler, it was a very rare event, and if that happened, everyone was notified and called, but as the language grew more and more complex, I saw that more and more, and it became a real problem because even if newer compiler doesn't have this specific bug, you can't always upgrade the compiler and you have to work around it. This specific bug was Clang-Tidy didn't like a method named malloc in a certain rare circumstances, or maybe not so rare, and we had to just rename this function to get Clang-Tidy to work. But to understand what bothering the compiler, you need to debug the compiler a little bit. You need to get stack traces, and you need to find out why is it crashing, because you have to work around it. That's one example. External libraries and tools you use sometimes crash, sometimes have bugs, sometimes you misuse them, but you still have to figure out what went wrong. And you find yourself having to debug a piece of code that you were sometimes wasn't even aware to its existence. Let's I'll walk you through my story, the certain bug I was trying to debug, and the problem was a crash in JVM in the Java. Now, I'm not going to talk about Java in C++ convention, but apparently Java is written in C++. So the code I had to debug is the C++ Java is written with. So Java crashed at a certain point. It wasn't supposed to crash. I thought I knew what the root cause was, and I wanted to figure out a certain value. This is this test over here. I want to figure out what the value of test was during this crash. That's what I was trying to do. As I said before, the best way to solve a problem is not having to solve it in the first place. So the best way to cope with a program you don't have debug symbols is to find them. And it's sometimes even easy. Microsoft had for years public symbol servers, which given an artifact, a DLL, it would give you debug symbol for this DLL. Linux recently followed suit with debuginfod, which is a similar tool. You can use the file utility on Linux on every SO shared object, and you can see build ID. You give this build ID to the debuginfo daemon. Recent versions of GDB knows to do that automatically, and you get debug symbols. And also in some Linux distribution, you could do some apt-get DNF or package management trickery to convince the package manager to give you the debug symbols for a certain package you already have, which can make your life easier. Another option, and I think you need to think about target audience of the software you're trying to use, you can search for nightly builds for the software package you're using, because nightly build, the audience, the people who are interested with nightly builds are the developers or the testers of this program, and they need debug symbols so many times, and in Java this is exactly the case. Nightly builds would have debug symbols to download, and you can use them, and the nightly builds could contain even a release build if you go back enough in time. And this was true in my case, and OpenJDK had in nightly build the debug symbols. And let me walk you through how did I use them, because it's not always... why do I need debug symbols? Because if you just use GDB, get a breakpoint, crash your program and get a backtrace, you wouldn't see the argument to the functions in the backtrace. You would just see the function names, because without debug info, it wouldn't know the signature for this function. And I wanted them in. I was hoping that dest would appear somewhere in the backtrace as an argument, or another argument I can infer the value of dest from, and that would solve my problem. But it's not so easy in 2 words. It's not so easy to use, or at least not so straightforward to use debug symbols. You have to first figure out the address that this is the libjvm, and this is the address it was loaded in your particular session, and then you need to add the symbol file to that you downloaded to this address. And then it worked. I got 2 things from that. I got in the backtrace inline functions, because it knows where the inline functions are, and I got all the values for the arguments. However, unfortunately, wherever dest occurred, it had 3 dots instead of its value, and it wasn't a string. We have progress, but it didn't solve my problem yet. Why is that? Because it was optimized out. These functions were probably inline functions, and the optimizer did a lot of modifications to the assembly so that the debug info was not enough to understand what the value of dest. Okay, so and it just don't work. Even if you put a breakpoint and you print the dest variable, it wouldn't work. Most people who debug program ran into that. So I still needed a solution for my problem. I still need to figure out the value of dest, even without the aid of the debugger. So I wanted to search for a ground truth for a certain points in time where I'll be very certain I know the variable that I can, the values of the variables I can deduce the value of dest from. And at least one ground truth is the calling convention. You know for certain that when you call a function or right after you called it at the beginning of the function, you would know where to look for the variable using the calling convention. In x86, these are the first 3 variables: d, rsi, and rdx. You put a breakpoint, you look for the registers, and you get the variables, whether or not the debugger assists you or not. So the plan was to break at some function higher up the stack with a variable that I can deduce the value of dest from, and then from this value I'll be able to find out what was the value of dest during the crash. The problem is that I can't really go back in time. And if I put a breakpoint and just look in the variable I'm interested with again and again, it wouldn't work, because this breakpoint happened too much. This function higher up the stack was called in different contexts much before the crash occurred, and it took too much time to just continue again and again and again when I ran into this function. Just as important as it is to report what worked for me, I'm going to report what didn't work, thing that I thought would work but didn't work, at least for me. This is a rule I have, that if something is hard to do, it just wouldn't happen. If there's a piece of software which is very complex to use, and I tried for a day to get it to work, and I didn't get it to work, even if I would get it to work eventually, it wouldn't work at scale for a team. It wouldn't be a tool that everyone would be able to use. Again, this didn't work for me. Maybe I didn't know something, but it's valuable to understand what didn't work. GDB record is supposed to be a back-in-time debugging facility available for everyone, but I couldn't get it to work. What you should do is you should put a breakpoint at a point in time close to the crash, issue GDB record, it should do its magic recording of events, and then you'll be able to step back and to put a breakpoint and continue back in time. Again, I couldn't get it to work on big complex programs. GDB trace is another option. It's supposed to let you put a trace point, print things to a memory buffer so that it will be very quick. You could put a trace point at a place that happens tens of thousands of times. And then when the program crashes, look at the trace log, the recent lines in the trace log, and you'll be able to see the variable upper header stack. But this is a small limitation. It wouldn't work with multi-threaded programs according to the documentation. And I don't see any program that it would be useful for me, but and it's definitely not useful for the Java virtual machine. So that didn't work as well. This is a trick that can work sometimes. Every breakpoint can be automated. You could put a print command and continue command at the breakpoint, and essentially get a trace, a log trace each time a certain breakpoint would occur. In my case, I could put a breakpoint upper the stack, put a command there to print the value of the variable I can deduce test from, and then tell the breakpoint to continue. And eventually, when the program would crash, I would look at the print log, but the problem is it's too slow. It could take milliseconds, and if it happens too frequently, it's so slow the JVM just doesn't function. Another trick that was useful for me is decompilation. Usually the source code is more readable than the assembly output, but the source code is not one-to-one equivalent with the optimized output. A nice anecdote is that at a certain point in time, the Intel documentation to x86 command was 800 pages, and this is the length of the C++ standard. So I'm not sure what's more complex. But sometimes, this is pretty approachable. You don't really have to use all the knobs in this. The tool I use is Jidra. It's open source and free, and you don't have to use all the knobs. You just find your functions, hit decompile, and you'll be able to see source code, which is sometimes more readable than the original C++ source code. To your right. Now, what do I do? How do I use it? I need to read the C source code to understand the equivalent line in the C source code to my C++ program, and then to understand the parameter I'm interested with. When I click this parameter, I'll see the equivalent register to my left that this parameter is stored in, and then I can see the address I can put the breakpoint. I can put a breakpoint in. You put a breakpoint in explicit address in GDB with asterisk, and then I can break at this command. I can look at R12 register, and I'll get the parameter, the best parameter I was looking for. This worked. This is another tool, as I previously mentioned. GDB trace didn't work, and it is sometimes useful to get a fast, efficient log at a certain points in the program. And the tool that enabled me to achieve that, and again, if in program we didn't write or are not able to compile, you can just put a print or an LTTNG trace in points that are of interest to you because the program is already compiled. And from bitter experience, it's not always easy to even compile things you have source code. If anyone want an anecdote is, I asked in the JDK main list, how do you compile JDK 8, which is pretty old but still very used, and no one was actually sure. They were asking again and again. I asked, which version of GCC do I need to use? Because in recent GCC, the compilation fails. And no one was quite sure, and then someone said, referred me to a GitHub repository where there are Docker files that one of them should be able to compile JDK 8. It's not easy to, even if you have the source code, even if you have the build environment, it's not always easy to compile. So Frida, the tool, it's mostly used for Android, but it's working in Linux as well. And the main trick is that you write JavaScript or TypeScript. Frida compiles it to assembly code, and Instrument modify the binary program to add whatever you like, but in our context, the useful thing it would add is prints. So let me walk through a small file very similar to what I actually used. Here you have to find the module, the shared object, which is of interest to you. This was in my case. You need to find out which function you want to instrument. This was a function. Note that you have to use the mangled value. You have to search for it in all the symbols in the module, and you have to figure out the mangled name. And then another point is that sometimes this libjvm is loaded dynamically, and if you would start your program, it wouldn't be loaded, and this module load wouldn't work. And the trick to overcome that is to instrument the dlopen command in Linux, or the equivalent in Windows. Take the event where every command is loaded, and then if only after you load the OpenJDK, do search for the module and do your instrumentation. And this is a useful trick. But let's say we have the module at hand and we loaded it. We can put the moral equivalent of trace point. We could intercept this address. What Frida would do, it would replace the assembly command at this address. If someone is interested in the inner details, he should look for Frida gum as in chewing gum. I don't know what's called like that. And this is the C implementation. And on enter, just do when the breakpoint happens, just log whatever you have in mind, and you can have access to all the registers, all the arguments, and it would happen in runtime. It would be pretty efficient. You don't need a debugger. It generally works. This is example output of Java, and here you can see do you remember the ANR? Oh, sorry. The ANR trace here appears right in your console. Another useful trick, if you already have using Frida, is unlimited hardware breakpoints. You can break on any access to a certain address, which is similar to a GDB watch point, but you're not limited to the 4 hardware registers that implement the watch point. The way Frida does that is by changing by cooperating with the operating system and change the permission of the page, catching segmentation fault, and doing whatever you told him to do on access. This again could be useful. Here we caught all accesses to a global variable. We search for the global variable and caught all access there. this is what we didn't show before. Using Frida is quite straightforward. You have to supply the script, supply the executable, and after -- the arguments to the executable, it will execute it and do the instrumentation in the script you supplied it. Here you can see the operation and the address that we pretend, but you can put whatever you have in mind. And again, it worked for me. It's fairly efficient. Java worked as a whole. To wrap it up, the first thing you have to do is to make your job easier. Search for whatever information you have on the library, whether it's old source code, the recent source code, debug symbols. You'll be surprised to find to see what you can find. You should plan ahead what's of interest to you, what you want the debugger to give you. The debugger is not a magic sauce that you sprinkle on a bug and it disappears. You have to understand what the debugger, what information the debugger should give you, and plan ahead. What I do is I try to debug with the most readily available approach, and then to use more and more complex approaches. And again, decompilation and tracing could work in complex bugs and traces. You don't have to read assembly. You have to have a very shallow understanding of assembly to use that. You just need to read C. That is. Thank you, everyone. I'll be happy to take questions.
What was the bug?
It was a real bug in JDK8. It was a very stupid mistake of using a pointer instead of dereferencing it in printf. And apparently it was a bug that was caught and fixed later, but the one who fixed the bug didn't understand that the bug is relevant to JDK8 as well. It was caught in JDK 9 or 11 in a test suite, but it happened before. And the fact it was caught in JDK 11, it was just because the test suite was added in JDK 11, but the bug happened before. And the workaround was not to use a debug mechanism to save Java events to file when it's done executing. We didn't modify Java, but it eventually worked. Thank you, everyone.